In this video, we'll discuss the value of an automatic charging relay in a boat that has two separate battery banks. We'll go into details of why it's useful, a little bit about how it works, and we'll take you along for a practical example of how we transition a boat from an old-style battery switch to a battery combiner. So here are my batteries. I've got three 100 amp hour AGM batteries. The two black ones are the house system, and then the green one is the start system. And here's my main battery switch. It's very conventional and old style. Off, one, both, and two. I'm sure most of you recognize that. And it's also got a cutoff switch that's downstream of the house system, so I can shut my house system off independently. Here's the old system in schematic form. You can see the batteries. These two circles represent the battery switch, and the downstream engine and house circuits are here. For clarity, I've drawn two circles and two dials to represent the switch, but you have to know that these two dials are concentrically bound together and they move as one. The important point is the way both batteries feed a single bottleneck supply line. So whichever banks are turned on will be drained to feed both the house and the engine circuits. Also notice how the alternator sends current backwards along these same lines to charge the batteries. So the switch needs to be set to both if you want to charge both batteries. What this means is it's annoying. Every time I turn the engine on or off, I need to send somebody down to turn that switch. And if I forget, especially if I'm at anchor, I could end up with a start battery that's so depleted I'm not able to start the engine the next morning. There is a skill component to it as well. If the crew member turns the dial through the off position when he's trying to get from one position to the other, the whole electronics have to reboot to get restarted, and it's not good for the alternator. So is there a better way? Yeah, have a look at this schematic. The layout is the same. We've got the batteries, the switch, and the downstream devices. Again, for clarity, I've drawn two circles to represent the switch, but of course these two arrows are mechanically bound together and they move as one. They can't be independently switched. The key point here is that the house and the engine electrics are completely independent. There's no downstream bottleneck where they join together. You've also got fewer options on the battery switch, just an on and off, and an emergency option right here to pair the two banks if you ever need to. For example, if the start battery were to fail or if the ACR were to die. Now let's look at the new charging circuits. Here's the house bank, here's the start battery, and the outgoing current mostly going down to the battery switch for all the downstream switched devices. On the incoming side, we've got the alternator input, the shore power charger, and the solar input, and all of these feed into one terminal block. That block is permanently connected through a fuse to the largest battery bank. You might think that this fuse controls incoming current, but the more dangerous problem is outgoing currents from short circuits. So that's why you want a fuse protect for wires to be right beside the source of battery power, not beside the alternator. Notice also the fuse bank for unswitched power for devices like the bilge pump, the clock, etc. So no matter what that source of charging power is, the ACR will detect that voltage and automatically close its switch to allow charging of the start battery. Likewise, when charging stops, for example when you turn the motor off or when the sun goes down, the ACR will detect sagging voltage on the joined sides and open the switch to separate the two banks. Wait, the start battery needs to have priority. It's the most important battery on your boat. Well, there's a problem with that, and it has to do with inrush current. When you're at anchor, it's not uncommon for the house battery to get spanked. Meanwhile, the start battery has nothing to do and remains fully charged overnight, with the ACR separating the two. Suppose your alternator is directly attached to the start battery. When you fire up the engine the next morning, the ACR closes the switch and you'll get a huge inrush of both alternator current plus whatever the start battery can give, with transient voltage and current spikes that can mess up your electronics and your lines. To make matters worse, you get a more common problem called relay cycling. Notice that when the ACR allows current to flow, there's a natural drop of voltage on the incoming side as the voltage readings on the two sides equalize. To avoid depletion of the good bank, the ACR is programmed to stop communication if after 30 seconds the common voltage is less than 12.75 volts. So especially with weak charging sources, you get this inefficient, stuttering on-off effect if the downstream bank is large and undercharged. If instead the incoming alternator wire is on the house side, you'll still get a controlled 100 amp inrush directly from the alternator to the house bank without having to go through the ACR. After a couple of minutes, there'll be enough of a surface charge on the still charging house bank that the ACR sees the requisite voltage to allow current through, by which time the difference between the two sides is a lot less and the inrush through the ACR is way lower. So having an ACR is a lot like having an extra crew member. A crew member is completely focused on his task, who never makes a mistake and never gets thirsty for more beer. It also allows seamless integration of various charging systems. So if you do this project, you're going to need two devices, a battery combiner here and a new battery isolation switch here. Now, Blue Sea call this one an automatic charging relay. Other companies call it a battery combiner or rarely a battery separator. I don't like the latter term since it's too close to the name battery isolator, which is a completely different bird. This device senses voltage on both sides, and if either side measures greater than about 13 volts, it closes a switch to allow current to flow from the high voltage side to the low side. When the voltage on the highest side drops below to about 12.5 volts, it opens a switch to stop communication between the two sides. Doing a project like this, you'll likely come across a few wires you can't identify. Here's another use for an inductive ammeter. I've clamped around the mystery wires, and then I start turning on devices to see what draws power. In this case, when I turn on the S-bar heater, suddenly this wire draws current. I'm going to move this to where it should be, downstream of the battery control switch and battery monitor on the house side. You need to be sure it's fused, and you need to verify that the upstream wires you tap into can handle the extra current. Now I'm going to show you how much current the starter motor draws. The way it's wired presently, the starter gets current from the batteries and a small amount from the alternator. Rather than trying to do the math, all I have to do is put the clamp around both wires with consistent orientation, and my multimeter shows total current. So if you've always wondered why a starter motor is the only wire in a vehicle that isn't fused, here's your answer. You'd have to choose a fuse so large it would be useless at preventing fires.
Whoa, 360 amps.
Well, before we make a decision about what kind of wires we need to sort out how much current they're going to be carrying. Now this is a Balmar alternator, and I can't find the serial number anywhere on the alternator. It has a separate voltage regulator, and we have a couple of clues. First is the appearance. It looks to be like a Series 6 alternator, and they come in either 70 amp alternators or 100 amp. Secondly, we've got a fuse here, and that's a 100 amp ANL fuse, and it's a short run between the alternator and the post in the starter motor, and of course that's inside the engine compartment. And the wires that they used is AWG4 wire, and so both of those features suggest that it's likely not going to be the 100 amp alternator, but I don't know for sure, and I can't rely on the assumption that what they did was meeting the standards of today. And so what I'm going to do today is I'm going to do a load test on this alternator and see how much current it can put out. This is a carbon pile load tester. I'm going to attach the two poles to the start battery, run the engine faster than about 2500 RPM, and dial up the amperage to a few hundred amps to cause the battery voltage to sag. That sag is going to cause the alternator to give it everything it has, and I'll measure the alternator output with my multimeter to see what it can do. So to my surprise, that little alternator was able to put out at least 91 amps, and if I'd pushed the RPM further, I might have been able to get it up to about 100 amps. On the other hand, I know that that 100 amp fuse is never blown, and so I'm looking for wires with an ampacity of somewhere in the range of 125, 130 amps. Let's size the alternator wire now. It's important to note that with this new design, I need to route my alternator wires all the way back to the house bank. It's no longer possible to use a short run to the start wire and piggyback on engine power wires feeding the engine the opposite way. When you're talking about sizing wires, the biggest derating in a boat is usually the voltage drop. It's much more apparent than it is in the AC world. There are two reasons for that. First, the significance of voltage drop is rated in percent drop, meaning that a 2-volt drop in a 120 volt circuit is often negligible, but a 2-volt drop in a 12-volt circuit is huge. The second reason is the fact that in a boat you can't use the motor chassis for the return path like you do in a car. In a boat you need wires going both ways, so your distance between source and device is usually doubled. We need to look at two tables. I got these from document E11 of ABYC conventions. You can find an old copy with Google, or you can find the most updated copy hidden behind a paywall at the ABYC. Let's do the voltage drop table first because that's going to be the limiting factor. The trick is to make sure you use the correct table. This is 3% and 12 volts. We go down here to 100 amps. My run is about 10 feet from alternator to battery, so the total distance will be 20. But also note that in this case the return path is huge, 2-aught wire, so this comfortably puts us into the AWG2 territory. Now let's look at the ampacity table. When I zip tie these cables together, they're formally bundled for about 6 feet. Notice in contrast with AC systems, the ground wire is calculated for this calculation, just as the neutral wire in AC systems is counted. So the right thing to do is to derate the ampacity for bundling by using table 6, 3 or fewer bundled DC conductors. The temp rating stamped on the marine grade wire is 105 degrees C. Even though there's only a couple of feet of wire inside the engine compartment, we need to follow the engine compartment derating. So we follow this column down to intersect with the AWG2 wire that we chose from the voltage drop table. We get 125 amps, so this gives me a reasonable cushion of about 35 amps over what I've shown my alternator puts out. AWG2 it is. We want a fuse that blows just below the ampacity threshold of the wire. 125 amps is fine. I'll run through a few shots of the assembly. This always seems to take longer than I think. I had to pull out floorboards to string wires. Here I'm using a hydraulic crimping tool to do my crimps. You can buy cheaper manual crimpers or even solder with gas if you like. I'm using marine grade lugs that are tinned in marine grade tinned wire. Here I'm fitting adhesive lined heat shrink for this with a heat gun. Here's a mistake. I used number 10 screws to mount the ACR and it seemed fine, but the heads protruded so far I couldn't get the cover on. This ACR has a cover with a couple of options to remove different flaps depending on how the wiring is routed. I used a box cutter to remove the appropriate flap. A power tool would have been faster. This is excellent aftermarket engineering. Not only is the hole perfect, the 4 mounting holes line up perfectly as well. So I can use the old faceplate with no new holes. Well, now that we have fuses at both batteries, we don't need this fuse by the alternator anymore, so I'm going to take it out. All right, now hold on a second. We've got a decision to make. This is my battery sense wire with a 1 amp fuse, and I need to decide where to put this. Now, to orient you, this is the input wire from the alternator, and it goes through this 125 amp A&L fuse to the house bank right here. And then this is the ACR, and it feeds the start battery. Now, you'd think that if I put the battery sense wire right on the battery, right on the house bank, that would work. But let's hold on a second and think about this. This is the fuse, and what it means is the input wire is separated from the battery sense wire with a fuse. Is that a problem? Well, if this fuse blows, the voltage regulator won't know, and it'll keep pumping juice into this node, and it won't be able to go anywhere, and so it'll back up into the start battery until the ACR shuts things down because of overload. So you need to put this battery sense wire as close as possible to the battery, but we're going to put it right here on the same stud that the input wire goes. Wait, what? Why not put the sense wire on the back of the alternator the same way it's done in a car? That thick wire goes to exactly the same place. You can, and it will work. In fact, it's the way most alternators are hooked up. But consider this example. Here's the alternator with its high output wire leading to the battery and the voltage regulator. I've drawn the sense wire to hook up to the alternator. Recall that we chose the alternator output wire to accept a 3% drop along its length during high output. The current flow is in this direction, so the higher voltage would be on the alternator side. Let's assume that your battery design calls for a voltage target during bulk charging to be 14.4, so the voltage regulator would be adjusting bulk stage output to achieve that. But look at the battery end. The battery end of the wire, you get 3% less, 14.0 volts. So your sense wires on the alternator, you're going to consistently undercharge in the initial stages. Yeah, but that thin sense wire has to stretch exactly the same distance. How is the voltage drop on a thicker wire so much worse? Yeah. Recall that voltage drop is a product of current and wire resistance, and current in that sense wire is 0.000053 amps, practically zero. And so the voltage drop in that sense wire is going to be almost nothing. So this little wire right here is the ground wire for the ACR. But in contrast with the normal ground wire, it's got a 1 amp fuse. And the reasoning behind that is that this is actually a switch. It's not so much of a safety ground. And so I'd like to know how much amperage this ACR is drawing, just in an effort to see if it might be responsible for some kind of parasitic drain. And I've set up my ammeter in line. And so we're just going to hook this up here and just measure how much current it draws. And so we're drawing 15 milliamps. That's pretty good. There, did you hear that? So as I suspected, once the two banks are paired, the ACR starts to draw significantly more. This is the main wire that leads from the alternator to charge the batteries, and it's got 24-hour-a-day power here, even if the battery switch is off, and so that's important. Before I started to work on it, there were 3 things attached here. There was this wire, there was a second wire which has a 10 amp fuse and goes to the voltage regulator, and that one's okay for it to be hooked up to unswitched power. And then there was this wire here, and I had to move this wire because this wire feeds the rest of the engine. And so I've stripped the loom back to allow me to get enough room, and I'm going to take it down to the B+ post of the battery. I'm going to tape this all up in a minute and get it all straightened out. Okay, the video is getting a little long, so I'm going to close it out here. There's lots more to talk about. I'm going to close with 2 final points. The first is that you need to double check your work. When the ACR is open, you need to see 2 distinct battery voltages on each side. Make sure that they're not running in parallel, because you need to make sure that there's no backdoor connection between the 2. And then my second point is that any charging system will have a minimum threshold below which it won't charge. If I look at my voltage rater for my alternator, it's 11 volts, and that could present a problem, say, in a marina somewhere. If I'm way off at an anchorage in, say, the Broughtons, and I really deplete that house bank, say, down to about 10.5 or so, the next morning when I start up my engine, the alternator may not be seeing the voltage it needs to verify that it's safe to charge. It may not charge. And so you need to make sure that that's going to happen. Fire up the engine, and while the engine is running, wait the 45 seconds and then make sure that you're getting charged down to that house bank. Now, if you're not, you've got a couple of options. The first is you could simply manually pair the two banks together, and that'd be easy enough to do. The second option is to use what I use, one of these things here. Now, I'm not sponsored by NOCO, and there are other companies that make this, but I'm happy with the one I have. These things are roughly equivalent to having an extra battery and some jumper cables, and you get to be a hero in the anchorage if you can help somebody out in the future. What I do in the context of an alternator that's not seeing the appropriate voltage is I simply hook it up to the battery and give it a bit of a charge, and then the alternator would see that charge and then take over from there. Say, if this video helped you out and you want to see more of them, then hit like or subscribe or leave a comment. I'd love to hear what others say. Thanks for watching.